Hello dear students, we are back again with another video lesson. If you remember, in a previous lesson, we studied the interference of the wave, section 4, chapter 3. So the wave can interfere because they occupy the same space at the same time. So the interference will occur in all types of the wave, including mechanical wave and electromagnetic wave. But the interference of the mechanical wave is much more advanced than the interference of the electromagnetic wave. So in the mechanical wave, so we can divide the interference of the mechanical in the mechanical wave into three different parts, such as constructive interference, destructive or weakening interference, and complete destructive interference. In the constructive interference, the two waves can interfere each other to produce the larger amplitude. In the constructive interference, the resultant amplitude is always larger than the individual amplitude. Okay? But in the second type of the interference, the weakening interference, the resultant amplitude is always smaller than the larger individual amplitude. Okay? And in the last type of the interference, the complete destructive interference, this type of the interference will occur when two waves with the opposite side of the displacement from the equilibrium position interfere with the same amplitude. In the complete destructive interference, the individual amplitudes must have the same value. Okay, so and if you remember, we stopped here, standing wave, another topic in section 4, chapter 3. Well, what is the standing wave? Standing wave, a wave pattern that results when two waves of the same frequency, same wavelength, and same amplitude travel in opposite direction and interfere in a given medium. This is the definition of a standing wave. Okay? As you can see in these figures, okay, so this is the standing wave. In the standing wave, the two ends must be fixed, okay. For example, if we have a string fixed at both ends, now there is no wave, okay. But in the case, for example, when we pull this string, what happened? The wave is produced, okay. This is standing wave. In a standing wave, the string must be fixed at both ends, okay? And sometimes you can get this type of the standing wave, okay? So this is the incident pulse, okay? Because the fixed end, the reflection of the wave at the fixed end, it's gonna be reflected, okay? So this is the incident pulse and this is the reflected pulse. This is the incident wave and this is the reflected wave. So that is why, according to this definition, standing wave, a wave pattern that results when two waves, okay, two waves of the same frequency, okay, the incident frequency and the reflected frequency is the same, and also they have the same wavelength and the same amplitude but travel in opposite direction. The incident wave is moving to the right, but the reflected wave is moving to the left, opposite direction, and interfere in a given medium. This is a standing wave. Standing wave in a string, we have many different types of the standing wave. We will talk and we'll explain in detail in chapter 4, section 3. But in this section 4 in chapter 3, only we will talk about the standing wave in a string. In a string, the standing wave occurs when the two ends of the string is fixed, okay? So you can find the value of the wavelength according to this equation. Wavelength is equal to 2L over A. This is antinode, okay? Or the number of antinode. The simplest standing wave in a string consists one antinode and two nodes. Okay, so we have two regions here. The regions with the zero displacement is called node. What is this? This is node. Okay, The node has zero displacement. The interference is completely destructive. And the other point is called anti-node. Okay, this is the maximum displacement above the equilibrium position. Is called what? Anti-node. This region is very, very important. Please pay attention. We have two different regions in the standing wave, node and anti-node. Okay, the node is the result of when the complete destructive will occur on a standing wave. Okay, we can say the node, and the anti-node in the case of the constructive of the wave is called anti-node. Okay, the simplest standing wave that occur in a string consists one anti-node and two node. What is this? This is the simplest standing wave. Okay, simplest standing wave. The simplest standing wave consists how many anti-nodes? Two nodes. How many nodes? Two nodes. How many anti-nodes? One anti-node. Okay? So, for the simplest standing wave, how can you determine wavelength? 2L over 1. Okay? So, lambda is equal to what? Is equal to twice the length of the string. As you can see here, the distance between these 2 points is equal to half wavelength. So half wavelength in this case, half wavelength is equal to what? The length of the string. Okay? So by rearrange the equation, lambda is equal to what? Is equal to 2L. Okay? So this 2L is based from this, proving according to this figure. Okay? In the simplest standing wave, wavelength is equal to twice as much of the length of the string. When does wavelength is equal to twice the length of the string? If the string vibrates with one antinode and two nodes. Once again, listen to me please. When does wavelength is equal to 2L, the twice of the length of the string, you have to say when the string vibrates with how many antinodes? One antinode. How many nodes? Two nodes. Okay? So this is the simplest standing wave that occurs in a string. Now I'm going to explain in detail to find the wavelength of the other case. Okay? Look, this is we have some certain frequencies produced by the standing wave. Okay? For the figure A, there is no standing wave. No standing wave. There is no wave. Okay? Figure B, this is the simplest standing wave. Consists how many nodes? Two nodes. How many antinodes? One antinode. Okay? The third one, figure C, how many nodes do we have? 1, 2, 3. Okay, the dot is represented for the node. The maximum displacement, how many antinodes do we have? 2 antinodes. Figure D, how many nodes do we have? 1, 2, 3, 4. How many antinodes do we have? 3. This is antinode, antinode, and antinode, and so on. Okay, look at this figure, figure 20. This photograph shows for 4 possible standing wave. Okay, how many standing waves do we have? We have 4 standing wave in this figure that can exist on a given string. Okay, and the figure B, the diagram shows the progression of the second standing wave for this one. Okay, the second standing wave in this figure for 1/2 of cycle. How many cycles do we have here? We have half cycle, or 1/2 of cycle. When the period is 0, look at this figure. It's very important, please listen carefully. Look at this figure. Okay, this is the second standing wave, this figure. We have antinode, 2 antinode, and 3 nodes. Okay, 2 antinode and 3 nodes. When the period is equal to 0, the amplitude has maximum value. But when the time increases, for example, when the time increases from 0 to 1/8, okay, 1/8 of this period, what happened to the amplitude? The amplitude decreases. Why? Because this is standing wave. In the case of the standing wave, the string is always moving up and down. Okay? So the amplitude gradually decreases when the time increases. Okay? After when the time is equal to 1/4 of its period, okay, what happened to the wave? The amplitude becomes 0. Okay? But the string does not stop. The string is moving downward in this case. In the first two case, the amplitude is located upward. But in this case, in this figure, look, when the period is equal to 3/8 of its period, its amplitude is going to be moving down. Okay? And when the period is equal to half of its period, when the time is equal to half of its period, the wave is going to be like that. Okay? And for the one complete oscillation, when the period is equal to 1 second, when the time interval is equal to period, it means that the string is moving back and forth. But in this figure, the string only is moving forward, not back. Okay? But for when the time is equal to period, the string must be moving one complete oscillation, moving back and forth. Like, for example, when you release in a simple pendulum, release a ball at the maximum displacement. When you release, what happened to the ball? The ball is moving forward. Okay, this is half cycle. But when it returns to its original position, it's gonna be one full oscillation. Okay. The definition of node: the points at which complete destructive. Node is a complete destructive. This is node. Zero displacement. Okay? Complete destructive. Zero amplitude, zero displacement. Interference happens are called nodes. Node in a string always is equal to antinode plus 1. Okay? N is equal to what? A plus 1. For example, in this figure, we have one antinode, the simplest standing wave. How many antinodes do we have? 1. How can we determine node by equation? Node is equal to A plus 1. A is equal to 1. 1 plus 1 is equal to 2. Yeah, we have 2 nodes. How can we determine number of nodes? Node is equal to antinode plus 1. So it means that in a standing wave in a string, number of node is always bigger than the number of antinode by factor of 1. For example, in a standing wave, if we have 30 antinodes, how many nodes do we have? We have 31 nodes. How can we determine number of nodes in a standing wave for the string? By using this equation. In the standing wave, for example, in a string, if we have 20 antinodes, how many nodes do we have? We have 21 nodes. If node is equal to antinode plus 1, antinode, by rearranging this equation, is equal to what? Number of node minus 1. Okay? Antinode, a midway between two adjacent nodes, located between two adjacent nodes. Okay? This is antinode, and we have 2 nodes here. The antinode is located between 2 adjacent nodes. The string, midway between the 2 adjacent nodes, the string vibrates with the largest amplitude at this point is called antinode, which is equal to number of node minus 1. What is the characteristics of the standing wave? What is the characteristics of the standing wave? In a standing wave, in the interference of 2 waves with the same frequency, same wavelength, and same amplitude, but travel in opposite direction. This is the characteristics of the standing wave. The interference of the 2 waves with the same frequency, wavelength, and same amplitude, but travel in opposite direction. What are the types of the interference in standing waves? In standing waves, we have 2 different types of the interference: complete destructive and constructive. The constructive interference produces, and we're gonna say an antinode. Antinode is a result of the constructive interference in a standing wave. Node is a result of the complete destructive of the standing wave between 2 waves. What are the types of the interference in the standing wave? We have 2 different types: constructive and complete destructive. Constructive produces antinode, but complete destructive produce node, which is the region of antinode and node. For the standing wave on a string, always the number of node is more than number of antinode by factor of 1. And also you can say, in a standing wave of the string, always number of antinode is less than the number of node by factor of 1. So we have some notes here about the standing wave. Look at these notes. The standing wave consists of alternating regions of constructive and destructive interference, as I mentioned before. The region of the constructive produces antinode and destructive is node. Okay? The longest wavelength, which means that the shortest frequency, the simplest standing wave that occurs in a string, is equal to 2L. What is the longest wavelength in a standing wave of the string? You have to say the longest wavelength will occur when the string vibrates with one antinode and two nodes. In this case, lambda is equal to 2L, and a number of antinode is equal to 1, n is equal to 2. Half vibration or half cycle of a standing wave includes 2 nodes, 1 antinode. Okay? Half vibration, it means that the simplest standing wave. 1 vibration, 1 complete cycle of a standing wave includes 3 nodes and 2 antinodes. The distance between a node and antinode is respectively is equal to 1/4 wavelength. So this is very important. The distance between a node and an antinode respectively is equal to 1/4. For example, this is standing wave, fixed at both ends. In a string, the standing wave in a string, the ends must be known, always. Okay, this is the incident wave and this is reflected and produces the standing wave. This is standing wave, okay? This is an example of the standing wave. How many nodes do we have? 1, 2, 3, 4. We have 4 nodes. Number of nodes is equal to 4. Antinode, 1, 2, 3. We have 3 antinode. Okay, we have 3. Number of antinode is equal to 3. Okay. The distance between node and antinode respectively, or the distance between antinode and node respectively, is equal to 1/4 wavelength. How? Look, this is node and this is antinode. As I told you in the previous sections, one wavelength or one complete oscillations consists how many quarters? 4. 1, 2, 3, 4. Okay? From node to antinode, how many quarters do we have? We have only 1. Okay? So that is why the distance between node and antinode respectively is equal to what? Is equal to 1/4 wavelength. Okay? The distance between node and antinode is equal to what? 1/4 antinode. Why? Because one wavelength consists of how many quarters? 4 quarters. The distance between 3 nodes is equal to what? Is equal to 1 node. One wavelength. Why? Because the distance between 3 nodes respectively consists how many quarters? 4. 1, 2, 3, 4. So that is why the distance between node and antinode respectively is equal to what? 1/4 wavelength. Okay? One wavelength has 4 quarters. The distance between 2 antinodes, look at node number 6. The distance between 2 antinodes respectively is equal to how many wavelength? Half wavelength. Why? Look. Okay, this is standing wave. The distance between 2 antinodes, this is antinode, and also this is antinode. The distance between two antinodes respectively. How many quarters do we have from this point to this point? The distance between two antinodes respectively. How many quarters do we have? Let's count. 1, 2. We have only 2 quarters. One wavelength requires how many quarters? 4 quarters. But in this case, how many quarters do we have according to this node number 6? The distance between two antinodes respectively, we have only 2 quarters, okay? So it means that we have half of wavelength, okay? Or you can say 2/4, we have 2 quarters from 4 wavelength. Or you can say 1/2 wavelength, okay? What is the distance between two antinodes respectively is equal to half of wavelength, okay? What is the distance between two antinodes respectively is equal to half of its wavelength. Node number 7, now I'm going to explain one by one in detail, okay? Listen carefully, please. The distance between two coherent or same phase difference antinodes respectively is equal to 1 wavelength. So this is completely different with the previous situation, okay? Be careful. When we say the distance between two antinode coherent or same phase difference antinode, it means that this two antinode has the same phase difference, okay? So it's gonna be reflect like that. This two antinode, when we say the distance between two coherent, in the coherent, in this case, it means that they have the same phase difference, okay? You have to skip the second antinode, okay? These two antinodes, this antinode and this antinode, these two antinodes, they have the same phase difference, okay? Why? Because for the second one, this is the reflected of the incident wave. That is why we have to ignore or skip the second one. If the question says, what is the distance between two antinodes with the same phase difference, you have to skip the second one, okay? You have to count only these two, okay? And also these two wave, this is also the antinode with the same phase difference. You have to skip this one. Okay, let's count the distance from this antinode to this antinode respectively with the same phase difference, okay? How many quarters do we have? 1, 2, 3, 4. Okay, how many quarters do we have? 4. 4/4 wavelength, 1 wavelength, okay? The distance between two antinodes with the same phase difference is equal to how many wavelength? 1 wavelength. But if the question says the distance between two antinodes without same phase difference, if the question does not mention the same phase difference, in this case, the distance between two antinodes respectively is equal to half wavelength. What is the difference between these two antinodes? Two coherent antinodes. In the coherent antinode, you have to skip the second one and you have to count these two antinodes, okay? The distance between two consecutive nodes is equal to half wavelength. The distance between two consecutive nodes, this is node and also this is node. Okay. The distance between two nodes respectively is equal to how many wavelength? How many quarters do we have? 2. Okay. In this distance, how many quarters do we have? 2. Okay. 2/4 wavelength. 2/4 wavelength, or you can say 1/2 wavelength. Okay. So we can say that the distance between two nodes respectively is equal to half wavelength. The distance between 4 consecutive coherent same phase difference is equal to 3 wavelength. Okay. Number 10, the distance between 3 consecutive antinodes, okay, without same phase difference. If the question does not mention the same phase difference, the distance between 3 consecutive antinodes, you have to add all antinodes, okay? This is 1 antinode, 2 antinode, and 3 antinode. The distance between 3 antinodes respectively, okay? This distance is equal to how many wavelengths? This distance is equal to 1 wavelength. Why? Because we have 4 quarters. One wavelength require how many quarters? 4. 1, 2, 3, 4. Okay, so that is why the distance between 3 consecutive antinodes is equal to 1 wavelength. Distance between 3 consecutive nodes is also equal to 1 wavelength. Why? Let's count. 3 nodes. Okay, the distance between 3 nodes, another figure. Okay, the distance between 3 nodes respectively also equal to 1 wavelength. Why? Now I'm going to show you. Okay, 1 node, 2 node, 3 nodes. Okay, how many quarters do we have? Let's count. 1, 2, 3, 4. The distance between 3 nodes consecutive or respectively 3 nodes is equal to 1 wavelength. Why? Because it consists 4 quarters. Okay, the distance between 4 consecutive is equal to 1.5. 4 consecutive nodes also equal to 1 over 5. So number 14, the standing wave that produced in a rope or string is equal to what? Is equal to 2L, 1L, 2 over 3L, and so on, okay? According this equation. Why? Because according this equation, lambda is equal to what? 2L over A. Okay? A is equal to what? 1, 2, 3, 4, 5, and so on, okay? If you replace L, wavelength is equal to what? Is equal to, when A is equal to 1. 2L over 1, 2L. Okay? This is 2L. The second one, 2L over 2. 2 with 2 cancel, what is remain? L. The third one, 2L over 3. 2 over 3L. For this one, wavelength number 4. 2L over what? Over 4. You can simplify. 2 over 4 is equal to 1 over 2L. Okay? For the fifth one, 2L over 5. 2L over what? Over 5. It means that 2 over 5L. Okay? So in the standing wave for the string, wavelength is equal to what? 2L, 1L, or 1 over 2 over 3 2 over 3L, 1 over 2L, 2 over 5L, 1 over 3L, and so on. Okay? The wavelength of the standing wave depends on what? The distance of the string. What does wavelength in the standing wave of the string depend on? The length of the string L and the number of antinodes. Okay? When the number of antinodes increase, what happened to the wavelength? Decrease at constant L. Okay? Once again, what is the relation between the length, wavelength, and the antinode? The relation between wavelength and antinode is inversely proportional at constant length of the string. In the standing wave, frequency of the standing wave is the same frequency of the source, and the amplitude of the standing wave is twice as much the amplitude of the vibrating source, because they produce the constructive interference. That is why it is amplitude gonna be twice. 2 antinodes represent crest and troughs. 2 antinodes represent what? Crest and trough. For example, this is crest and this is trough, and the 2 antinodes represent the crests and the troughs. Okay? A standing wave cannot be formed unless it allows the 2 ends to be formed at both ends. Okay? Nodes must be formed at both ends for the standing wave in a string, which means that the standing wave can be produced for any wavelength that allows both ends of the string to be node. The 2 ends must be what? Must be nodes. Always. In a standing wave for the string, the ends always must be node. The figures below show the 3 possible standing waves for a given string. In the figure A, there is no standing wave because the string does not vibrate. In the figure B, how many antinodes do we have? 1 antinode. How many nodes do we have? 2 nodes. Wavelength is equal to what? Wavelength is equal to 2L over A. For the figure B, how many antinodes do we have? 1. 2L over 1. Lambda is equal to what? Is equal to 2L. L is equal to what? 1 over 2 wavelength. For the figure C, how many wavelengths do we have? 1 wavelength. Okay? How many quarters do we have? 4. 1, 2, 3, 4. So that is why wavelength is equal to L. But in this case, we have 2 quarters. Half wavelength is equal to L. That is why wavelength is equal to L. For the last figure, the two ends must be known in the standing wave for the string. Always. How many antinodes do we have? 3. 1, 2, 3. Wavelength is equal to what according to this figure? Wavelength is equal to 2L over A. According to this figure, how many antinodes do we have? 3. Wavelength is equal to what? 2 over 3L. What about L? Is equal to 3 over 2L. 3 over 2 wavelength, sorry. Okay? In a given string, when does the wavelength of a standing wave is equal to twice as long the length of the string? In a given string, when does the wavelength of a standing wave? When does wavelength? The question says, when does wavelength is equal to what? Twice as long the length of the string. When does this happen? If the wave vibrate, or if the string vibrate with how many antinodes? 1 antinode. How many nodes? 2 nodes. When the string vibrates 1 antinode or 2 nodes. Okay? In a given string, when does the wavelength of a standing wave is equal to L? When does wavelength is equal to L? If the string vibrates with how many antinodes? 2 antinodes. How many nodes? 3 nodes. Why? Because if we have 2 antinode, 1, 2 with 3 nodes, we have 1 wavelength. So that is why wavelength is equal to L. In a given string, when does the wavelength of the standing wave is equal to what? Is equal to 2/3 the length of the string when the string vibrates with 3 antinodes and 4 nodes. So this is the wavelength over L, as I mentioned before, in the nodes, is equal to what? Is equal to 2, 1, 2 over 3, 1 over 2. Okay? Look at this question. Which of the following wavelength will produce the standing waves on a string that is 3.5 meters long? Okay? Be careful. In the standing wave, the number of antinodes, it must be integer number. What do you mean by integer number? According to Math Basic, the integer number or integer number must be 1, 2, 3, 4 until infinity. Okay? Without 0, without decimal. So the antinode must be integer number. What do you mean by integer number? Like 1, 2, 3. Not allowed 1.5, 1.3, 2.3. Okay? It must be an integer number. Okay? To find which of the following wavelength can produce the standing wave, we have to find number of antinodes. If the number of antinodes is integer number, we can say this wavelength can produce the standing wave. But in the case, if the result of the antinode is not integer number, like a decimal number, like 1.4 or the fraction, we cannot say this is produce a standing wave. Which of the following wavelengths? How many wavelengths do we have? 4. Very good question, okay? It is a Wizari question, be careful. Which of the following wavelengths will produce standing wave? How can you determine which wavelength produce standing wave? You have to find number of antinodes. If antinode is equal to 1, 2, 3, 4, and so on, we can say this wavelength can produce standing wave. But point, no. Okay? Look, which of the following wavelength can produce standing wave on a string that 3.5 meter long? L is given 3.5 meter long. Okay? For the first one, listen carefully, please. A, wavelength is equal to what? 1.75 meter. For the wavelength, it's possible with the decimal like 1.7, 1.2, it's okay. But for antinode, cannot be said, okay? It's not allowed the antinode results with the point like 1.3, 1.4. In that case, standing wave not produced, okay? When lambda 1 is equal to 1.75, how can you determine antinode? Okay, we have to find what antinode? Look, A is equal to what? According to this equation, wavelength is equal to 2L over A. If you rearrange this equation, A is equal to what? 2L over wavelength. 2L, do we have L? Yes, 3.5. Do we have wavelength? Yes, wavelength number 1, 1.75. 2 times 3.5 is equal to 7. 7 divided by 1.75 is equal to 4. This 4 is integer number? Yes. So, can we say this wavelength produce? Yes, of course. Produce standing wave. Why? Because A is integer number. Because A is what? Integer number. For the second one, B. Wavelength number 2B is equal to what? 3.5 meter. L is the same, okay? 3.5 meter. A is equal to what? To find whether this wavelength produces standing wave or not. Lambda is equal to what? 2L lambda to 2L over A. Okay? A is equal to what? 2L over lambda. 2 times the distance of the string is constant for all situations. Okay? Wavelength number 2 was given 3.5. 3.5 cancel. What does remain? 2. Antinode is 2. Is this wavelength produce the standing wave? Yes, of course. Why? Because antinode is an integer number. Okay? For the branch, for the C, okay? Wavelength C. Number 3 is equal to what? 5 meter, okay? L is already 3.5 meter. A is equal to what? Lambda is equal to 2L over A. A is equal to what? 2L over lambda 3. 2 times 3.5 divided by 5. Lambda 3 is, A is equal to 7 divided by 5, which is equal to 1.4 meter. Is this antinode integer number? No, this is not integer. So that is why this wavelength cannot produce, will not produce standing wave. This one, when wavelength is equal to 5 meter, when wavelength is equal to 5 meter, is this wavelength produce the standing wave with the length of the string? No. Why? Because the result of the antinode is not integer number. Okay? Because it is a point 1.4. 1.4 cannot produce the standing wave. The last one, D, wavelength is equal to what? 7 meter. L, 3.5 meter. A is equal to what? According to this equation, wavelength 2L over A, 2 times 3.5 divided, we have to rearrange. A is equal to what? 2L over lambda 4. 2L is equal to 2 times 3.5 divided by 7. 2 times 3.5, 7 divided by 7, 1. A is equal to what? Is equal to 1. Is this wavelength can produce the standing wave? Yes, of course. The last one will produce the standing wave. Why? because A is 1. Okay. We finished this section, and now we're gonna solve the questions of the section review, section 4 in chapter 3. Question 1: a wave of amplitude 0.3 meter, this is A, interferes with the second wave of amplitude, this is A1, this one is A2, and of the same direction from equilibrium position. It means that the two waves, both of the waves crease or trough. In the case when the two amplitudes have the same direction, we have to add up to find the resultant amplitude. Okay? What is the largest resultant displacement we have to add? 0.3 plus 0.2 is equal to 0.5 meter. Why we have to add? Because in the same direction. In the same direction of the amplitude produces what? The constructive interference. In the constructive interference, we have to add the two individual waves. Question 2, a string is rigidly attached. Rigidly attached, it means that a fixed boundary. Okay? It is a fixed boundary. Okay? A string is rigidly attached to poles at one end. Several pulses of amplitude 0.5. Okay? For example, if we send 0.15, sorry. Send down a string are reflected at the poles and travel back down the string without the loss of amplitude. What is the amplitude at a point on the string where the maximum displacement points of the two pulses cross? What type of interference is this? This is the incidence pulse, because the end is rigidly attached. What do you mean by rigidly attached? It means that fixed boundary. What is this? This is fixed boundary. How did you know this is fixed boundary? Because the question says rigidly attached. It means that fixed. In the case of the fixed boundary, okay, 0.15, and also the reflected ray is gonna be 0.15. In the fixed boundary, the types of the interference is complete destructive, please. Is what? Complete destructive. In the case of complete destructive, a resultant amplitude is always equal to 0. The answer is what? 0. The type of the interference is what? Completely destructive interference. Question 3. What would be the amplitude of the pulse in item 2? The question 3 is related with the question 2. In the item 3, question 3, what will be the amplitude of the pulse item 2 if the same pulse were sent down a string whose end is what? Free. If the end is free, okay? If the end is free, the type of the interference is gonna be constructive interference. Why? Because the standing wave, the reflection of the wave in the free boundary produces constructive interference. In the constructive interference, we have to add the individual amplitudes. Okay? The same amplitude of the item 2, we have to use the same individual amplitudes of the item 2 was given 0.15, 0.15. We have to add up is equal to 0.3. So the difference between question 2 and question 3. In question 2, the end is rigidly attached, fixed boundary, but question 3 is a free boundary. For the fixed boundary, resultant amplitude equal to 0 because we have to subtract the individual amplitude. But question 3, because the end is a free boundary, that is why produces the constructive interference. And to find the resultant amplitude, we have to add the two individual amplitudes. Question 4. A stretched string fixed at both ends is 2 meters long. This is L. What are the 3 wavelengths that will produce standing waves on this string? Name at least one wavelength that will not produce the standing wave pattern and explain your answer. In this question, you have to assume that because the L is given, L is equal to 2 meters. Describe the 3 possible standing waves. For example, when A is equal to 1, A is equal to 2, A is equal to 3, okay? So this antinode will produce the standing wave, and its wavelength is equal to what? 2L over A. 2 times 2 over 1, 4 meter. When amplitude antinode is equal to 2, wavelength is equal to 2L over A, 2 times 2 over 2, which is equal to 2 meter. Okay? When does the standing wave will not produce? If you can write up to you, okay? When A is equal to 1.5. When A is equal to 1.5, no standing wave will occur. Okay? Wavelength that will produce standing waves includes 4 meter, 2 meter, 1.3. Any value that doesn't allow both ends of the string to be nodes is acceptable. Minimum number of antinode 1, minimum number of node is 2. Okay, so this is homework. Okay, you have to solve this question by yourself. The 3 meter long straight string is fixed at both ends. If the standing wave with a wavelength of 2/3 of L, the wavelength, okay, I'm going to help you in this question. Wavelength is equal to what? 2/3 of L. How many nodes will be formed? You have to find number of nodes. Okay? Find number of nodes. This is the question of the standardized test prep, chapter 3. Okay. Question 1. A mass is attached to a spring and moves with the simple harmonic motion. We finished at chapter 3. Now we're going to solve the question of the standardized test prep that related with 4 sections in the chapter 3. A mass is attached to a spring and moves with the simple harmonic motion on a frictionless horizontal surface. We have to base your answers to question 1 until 5 on the information below. In what direction does the restoring force act? Okay, look at this question. Mass attached to the spring and moves with a simple harmonic motion on a frictionless horizontal surface. In which direction does the restoring force act? Because the direction of the applied force, it does not indicate it in this question. So to the left, no. To the right, no. To the left or to the right. According what? According on whether the spring is stretched or compressed. In this figure, we cannot say this spring is compressed or stretched. Okay? But if the spring is compressed, for example, this is the applied force when the spring is compressed, the direction of the restoring force is to the right. In the case of the stretching, the direction of the restoring force is going to be left. But in this question, because the compression and the rarefaction stretched region does not indicate, that is why we cannot say the restoring force to the left or to the right. C is correct. In what form is the energy in the system when the mass passes through the equilibrium position? When the mass passes through the equilibrium position, all the elastic potential energy converted to the kinetic energy. So the answer is C. Why? Because the question says passes through what? Equilibrium position. When the object in a mass spring system passes or reaches the equilibrium position, its energy is kinetic energy. In what form is the energy in the system when the mass is at maximum displacement? When the mass is at maximum displacement, restoring force maximum, acceleration maximum, elastic potential energy maximum. Elastic potential energy is stored when the spring stretches to the maximum displacement or compresses to the maximum displacement. Which type of energy is stored? Elastic potential energy. Be careful. Elastic potential energy, okay? A is correct. Which of the following does not affect the period of the mass spring system? The period of the mass spring system, period, you have to write down the equation of the period, 2 pi m over k. In the mass spring system, the period depends on the mass and the spring constant. But the question says does not affect. Mass effect, yes effect. Spring constant effect, yes effect. Amplitude, do we have amplitude? No, we don't have amplitude. So amplitude does not affect the period in a mass spring system. The answer is C, okay? If the mass is 48 kilogram and this is M mass and this is K, what is the period? Just replace, okay? I solved it and I showed all the works. Base your answer question 6 till question 9 on the information below. A pendulum bob changes from string and moves with the simple harmonic motion. Okay, this is harmonic. What is the restoring force in the pendulum? The restoring force in the pendulum, as I mentioned in the section 1, okay, this is Ft. This is Fg. Okay, because this is like inclined, this Fg, this is y-axis, this is x-axis. Because this Fg is not on the x-axis and y-axis, it makes an angle. Okay, so that is why this gravitational force can be resolved into two components, Fgy, Fgx. The Fgx component be a restoring force in a simple pendulum. Okay, Fgx is the tangent of the direction of the ball. Okay, the total weight, no. The component of the bob's weight tangent to the motion of the bob, yes, of course. So B is correct. Okay. Question 7. Which of the following does not affect the period of the pendulum? The period of the pendulum, you have to keep in your mind, period of the pendulum is equal to 2 pi L over G. What does period in a simple pendulum, what does the period in a simple pendulum depend on? It depends on the length of the string and the free fall acceleration. But the question says it does not affect. Be careful. The length affected the period? Yes, of course. The mass of the pendulum ball depend? No, does not affect it. Which one is correct? B is correct. Okay? Which of the following does not affect the period in a simple pendulum? The mass of the pendulum. Why? Because we don't have mass in this equation. The period in a simple pendulum depends on two factors: length of the pendulum and the free fall acceleration. Okay? Question 8. A pendulum completed exactly 12 cycles in 2 minutes. This is very good question, guys. Be careful. Please pay close attention. Question 8. The question says a pendulum completes exactly 12 cycles in 2 minutes. Number of vibrations. How many vibrations do we have? 12. In how many seconds or minutes? 2 minutes. This is T small. This is interval. Why? Because we have more than one cycle. T is equal to 2 minutes, but you have to convert this minute to second, which is equal to 120 seconds. Okay? Use this 120. What is the frequency of the pendulum? The frequency of the pendulum, we cannot use 2 pi radical L over G. Why? Because we don't have L in this question. And also we cannot say frequency is equal to 1 over period because we don't have period. So what we have to do, you have to use this equation. Frequency is equal to number of vibration over time interval. If the number of vibration is given, you have to use this equation. How many cycles do we have? 12 divided by 120 and is equal to 0.1 hertz. Okay, this is question 8. Question 9, a pendulum's length is 2 meters. Okay, this is question 8. Question 9, the pendulum's length is 2 meters and free fall acceleration is 0.8 meter per second square. How many complete oscillations does the pendulum make in 5 minutes? Frequency is equal to what? Number of vibration over time interval. Number of vibration is equal to what? You have to rearrange. Frequency, time is time interval. Do we have time? Yes. 5 minutes, which is equal to 300 seconds. Do we have frequency? No. How can you determine frequency? Frequency is equal to 1 over 2 pi G over L. The frequency of the simple pendulum is equal to 1 over 2 pi G over L. Do we have G? Yes. Do we have L? Yes. Replace and you can find number of vibration. Okay. What kind of wave? Base your answer question 10 till question 12. What kind of the wave does this graph represent? This is because this is displacement. Okay. If you see the displacement here, the type of this wave is transverse wave. A is a transverse wave. which later on the graph is used for the wavelength. C is wavelength, okay? Which later on the graph is used for the trough. A, trough. B is crest. D is amplitude, okay? Base question 13 till 14, the passage below. A wave with the amplitude. This is very easy question, okay? We have two amplitude, 0.75, 0.53. What is the amplitude resultant wave interference constructive? In the case of constructive, you have to add together, but for the destructive, you have to subtract, okay? Question 15 is like a question 12, question 9. You can find the speed of the wave, and also question 16, it is too easy. You have to find the frequency, after that the period, okay? We finished this chapter. Thanks for listening. Keep up your best doing. Inshallah, see you in the next chapter, chapter 4. Thanks for listening. Goodbye.